All right, moving on. The next gas law we're going to look at is Gay-Lussac's law. This law looks at the relationship between pressure and temperature. It's kind of a piggyback off of Charles' law. In Gay-Lussac's law, we say that the pressure of a gas at standard temperature and pressure is directly proportionate to the temperature of the gas. Very similar again, directly proportional. So if I increase the temperature, I should increase the pressure. Now, Charles' law said that if you increase the temperature, you would increase the volume. So they're talking about a container that allows for expansion. Obviously, if the volume changes, like the shape and the size of the container needs to change. The difference here with this Gay-Lussac's law is that you will have constant volume. And like all the other ones, number of particles. Okay, so this Gay-Lussac's law is usually studied in reference to what they call a rigid container. A rigid container is one that does not allow for expansion. So something like glass or metal. I don't love the picture here with a balloon. I usually think of a balloon for Charles' law. If I increase the temperature, the balloon should expand. If I decrease the temperature, the balloon contracts. It gets smaller. So I don't love the balloon. I'll deal with it. But we're trying to show that if I have a constant volume, let's say it's a glass beaker or some kind of a container that is rigid, it does not allow for the volume to change, and I increase the temperature. I increase the temperature, the particles still have more kinetic energy, which means more collisions. But now, if those collisions cannot create a larger volume, the container cannot expand to keep the internal pressure constant. Well, now, if you got more collisions, you're just going to see an increase in pressure if the container cannot expand. So I guess what they're trying to show in this picture is that if I increase the temperature, so I don't know, the mercury is rising, the temperature is going up, and these particles inside the balloon are colliding with the walls of their container, and at some point, I don't know, the internal pressure becomes too large, and the balloon pops. I'll get over it. It's not my favorite example. I usually like to think of, again, something metal or glass. Like if I had a glass tank, like a metal tank. I don't know. So maybe this is like a, this is a metal tank. Metal gas tank. And I have gas, some kind of gas inside the container. It does not matter the identity of the gas. None of these gas laws really do. We're just concerned with the number of particles and then their conditions, such as temperature, volume, pressure. So this would be the type of container that's rigid. And if I increase the temperature of the gas particles inside of this tank, yeah, they're going to increase in kinetic energy and they're going to bounce all over the place. And they're going to have more collisions with the walls of their container. But the metal gas tank will not expand in volume, so I'm just going to see an increase in pressure. We're going to do this in the lab with a metal flask, and we'll have a stopper on the top. If you increase the temperature too rapidly or too extremely, this rubber stopper will pop off, where the internal pressure will become too great. And I guess the other option is to break the glass flask, and I don't really want that. It is possible in the lab that you could pop the rubber stopper out of your flask. So we'll have a setup in the lab that kind of looks like this. Ooh, flask. That's not bad. And then there'll be like a metal stopper, rubber stopper on the top. So it is a closed container such that the number of particles is always constant. Because again, if I had a leak of some kind, I could be increasing the temperature. The particles have more kinetic energy. They're moving faster, but they find this little leak, and so out they go. And then I don't really see an increased pressure because I'm losing gas particles. With it being a directly proportional relationship, the graph will look just like Charles' law. And again, we're going to graph these in the lab, so we should be able to create this. My highest temperatures will create the largest pressures, and vice versa. My lower temperatures will create lower pressures. And notice again, Kelvin. To study this in the lab, you must use temperature in Kelvin. So the formula, the equation, looks very similar to Charles' law. I'm going to give you that. But it's pressure over temperature instead of volume over temperature. When I think of directly proportional relationships, the equations always look real similar. The variables are directly on top of each other. P1 over T1 equals P2 over T2. Easy. I mean, this is just basic algebra, solving for these variables, little proportions. I get it. I mean, eventually there's kind of a lot of little equations, so I'm going to give you that. You'll just need to know when to use it and how to use it. All right, so it's going to look like this. Just like all the other little gas laws, I want to look at the data I'm given to see what kind of variables I have. I mean, here it's easy. Like, obviously, duh, this is going to be Gay-Lussac's law. But when you see these on a test or quiz, they'll all be jumbled up. So, I mean, the first one could be Charles' law, and then you have a Boyle's law, and then a Gay-Lussac's law. And that's when people usually freak a little bit. But they'll say, I mean, I can do these if you tell me the equation. Well, that's no fun, right? Because if they're all jumbled up, just look at the data that you have available. A sample of oxygen gas exerts a pressure of 2.5 atmospheres on the sides of its container at a temperature of 45 degrees Celsius. If the temperature were to increase to 56 degrees Celsius, what would be the new pressure? Okay, so my variables are atmospheres, and then I see some Celsius. And so in my head, I need to know that atmospheres is a unit of pressure and Celsius is a unit of temperature. And then there I have my equation. Pressure, temperature, P1 over T1 equals P2 over T2. That's on the test. I'll give you that. The variables that we're looking for in a nutshell, pressure, could obviously be the atmospheres, ATM, kind of an English unit of pressure. It could be metric, Kilopascal. It could be that millimeters of mercury, which is the same as a torr. Equivalent units. Any of those are acceptable pressure units. But then again, your temperature. In any gas law, in order for the results to be accurate in the lab, your temperature must be in Kelvin. Must be Kelvin. And so again, I'll show you on the test the conversion between Celsius and Kelvin, which you're going to use a lot. I mean, in the lab, we're going to measure Celsius. Our thermometers measure Celsius. And so we'll just do this quick switch, and away we go. Okay, so let's set it up. P1, my initial pressure, 2.5 atmosphere. My initial temperature is 45 degrees Celsius. I'm going to go ahead right away and add the 273. 45 plus 273, 318 Kelvin. Not 45 degrees Celsius. All I did was add the 273 right away to switch it to Kelvin. Okay, what am I doing here? The temperature increases and I want to know the new pressure. That's the P2. So I'm going to take my 56 degrees Celsius and add 273, 329 Kelvin. Not 56 degrees Celsius. I mean, you can do it on paper, you could do that. But then if you really try to verify this in the lab, you will not have the correct pressure. So we cross multiply. In my calculator, I'm going to go 329 times 2.5. And then I'll divide by the 318. Okay, so my pressure, P2. The original pressure is 2 sig fig, so I'll leave 2. 2.6. Interesting. Okay, number one, it makes sense. I increased the temperature, so the internal pressure should increase. It's got to be something greater than 2.5. But if you look at this in Kelvin temperatures, I increased the temperature, but not drastically. 318 to 329. That's a slight increase. So the pressure should go up, but it shouldn't be crazy. So if this were, again, a multiple choice question and your calculator dies, I think you could probably pick a reasonable answer. Okay, number one, if you increase the temperature, the pressure needs to increase. So any answers less than 2.5 are not correct. I increased the temperature slightly. So my pressure should increase slightly. Something slightly greater than 2.5. So if any of the choices were like 10 atmospheres, that's probably too high. Isn't this great? Are you feeling confident? Like, yeah, I can do this. All right, so the second example gives me a 250 milliliter sample of butane gas that exerts a pressure of 255 kilopascal on the walls of a butane lighter at a temperature of 28.5 degrees Celsius. At what temperature would the pressure increase to 300 kilopascal? Okay, so let's pretend that I don't know what law to use. I mean, obviously it's in the Gay-Lussac's law section. Let's pretend I don't. And so I look at my variables. I look at my units specifically. 250 milliliters is a volume. Exerts a pressure of 255 kilopascal. So I've got a volume, I've got a pressure, and I've got a temperature. Oh, brother. I've got 3 variables, and all of these little gas laws only compare 2 at a time. One of them is irrelevant. So let's look at what they're really asking me here. At what temperature would the pressure increase to the 300 kilopascal? I'm not changing the volume. I mean, like a little butane lighter is a constant volume. It's like a rigid container. It's a plastic, usually plastic metal container. It doesn't allow for expansion. So the 250 milliliter container sample, it's irrelevant. And we're not changing the volume. We're looking at the relationship between temperature and pressure. Ha, tricky. Didn't trick us. Okay, so I have an initial pressure of 255 kilopascal. The temperature is 28.5 degrees Celsius, so I'm going to add 273 right away. 273. 301.5 Kelvin. So not 28.5 degrees Celsius. I'm thinking about that, but I need to switch it to Kelvin. At what temperature would the pressure increase? So I'm increasing the pressure to 300 kilopascal. And I'm solving for T2, the initial or the final temperature. So cross multiply and plug this in our calculator. So it's pretty simple algebra. Okay, so T2. Oh man, okay, so my initial temperature, I don't know, is somewhere between like 3 and 4 sig figs. I'm not gonna pick like crazy on your sig figs here, as long as you leave something reasonable. I mean, don't give me 10 decimal spots. I mean, in Celsius, the temperature had 3 sig figs. In Kelvin, it kind of adds a fourth. 3 or 4, either of those would be fine. Maybe I'll just go 3. Cross multiply. 350, I'm going to say 5 Kelvin. And there she is. So I want the pressure to increase. I need to increase the temperature. And so if I used Kelvin in my equation, my temperature, my final temperature will come out in Kelvin. Now there is a multiple choice question that you'll see sometime in your future, where it's a simple setup, something similar to this. You're solving for the final temperature, and all of the choices are, heaven forbid, all of the choices are in Celsius. And they're trying to trick you into thinking, well, gosh, if all the choices are in Celsius, then I guess I can use Celsius in my setup, in my calculations. No. I still need to switch it to Kelvin when I do my math. But now if by chance all of the answers are back in Celsius, because, I mean, in the lab we would realistically be measuring with a Celsius thermometer, then all you gotta do is subtract the 273, and you can bring this back to Celsius. So this would be equivalent to like 82 degrees Celsius. So maybe the 82 degrees Celsius would be the answer that you would choose on a multiple choice question. So the calculation still needs to be done in Kelvin. If I were to try to do that calculation with a 28.5, I mean, if you really want to, you can pause the video now and try it. But you're not going to get 82 degrees Celsius. So you still need to do the calculation with Kelvin. And then if they really wanted the final temperature back to Celsius, just subtract the 273, and you got it. And there's nothing else that could make this Gay-Lussac's law any more difficult.